What is a separable differential equation and how we can solve such differential equations? A first-order differential equation of this form is said to be separable or to have separable variables. In these types of differential equations, we can rewrite them in this form. And then we can integrate both sides of the differential equation to find the solution. Here is an example of a separable differential equation. We can rewrite this differential equation as dy over y is equal to dx over 1 plus x, and now we can integrate both sides. Then on the left-hand side, we will have ln of the absolute value of y is equal to ln of the absolute value of 1 plus x. And then we will have a constant of integration, which we call it c1. And if we exponent both sides of the equation, we will have e to the power of ln of 1 plus x plus c1 on the right-hand side. We can rewrite the right-hand side as e to the power of ln of 1 plus x times e to the power of c1. Here, the first term will be equal to the absolute value of 1 plus x, and e to the power of c1 itself is another constant, which we call it c. And from here, we can say that y is equal to plus minus c times 1 plus x. And since plus minus c is a constant, we can just write c here. And this is the solution to the given differential equation. Now let's solve some examples for the separable differential equation. So this differential equation is a first-order differential equation. And as we can see on the right-hand side, we have e to the power of 3x plus 2y, which we can rewrite it as e to the power of 3x times e to the power of 2y. So we have a function of x times a function of y, and we can separate this differential equation. And if we rewrite this differential equation, we will have dy divided by e to the power of 2y is equal to e to the power of 3x times dx. Or we can rewrite it as e to the power of minus 2y times dy is equal to e to the power of 3x times dx. And now we can just simply integrate both sides of this differential equation. So the integral of the left-hand side is minus 1/2 of e to the power of minus 2y. And the integral of the right-hand side is 1/3 of e to the power of 3x. And we have the constant of integration, which is c. And this is an implicit solution to the given differential equation. Here is the second example, which again we have first-order differential equation. Now let's rewrite the right-hand side of the differential equation. And if we multiply this differential equation by x squared and divide it by y, we will have this differential equation. Which is clearly a separable differential equation. And we can expand y plus 1 squared. Whereby integrating both sides of this equation, we can find the solution. Whenever we have the multiplication of a polynomial and a logarithmic function, we need to use the method of integration by parts. So we will call ln of x u, And x squared dx, we'll call it dv. So u is ln of x, and dv is x squared dx. Now we can find du, which is 1 over x dx, and v is 1/3 of x cubed, where we know that the solution when we're using integration by parts, it's that the integral of u dv is equal to uv minus the integral of v du. So now if we plug these into this integral, we have u dv is equal to uv minus the integral of v du. So we can rewrite this as this equation. So the integral of x squared ln of x dx is equal to 1/3 of x cubed ln of x minus 1/9 of x cubed plus the constant of integration. Now we can substitute this result back in here. And now we can integrate the right-hand side. And now we can combine C1 with C2 into C. Which is the implicit solution to the given differential equation. Here again, we have a first order differential equation, but now we have a boundary condition. So we need to find the constant of integration here. We can factor the right-hand side and rewrite the differential equation. And divide both sides by 1 minus x. And clearly this is a separable differential equation, and now we will separate the variables. Here we need to integrate both sides. Now we can use this condition to find the constant of integration c, where x is equal to -1, y will be equal to -1. So ln of the absolute value of -1, which is 1, is equal to -1 divided by -1, minus ln of the absolute value of -1, which is 1, plus c. And we know that ln of 1 is equal to 0. So from here, c is equal to -1. Again, this is the implicit solution of the given differential equation. However, here we can find the explicit solution by exponenting both sides. On the left-hand side, we will have the absolute value of y, and we can simplify the right-hand side as e to the power of -1 over x minus 1 times e to the power of minus ln of x. where e to the power of minus ln of x is 1 divided by x. So this is the explicit solution of the given differential equation.